Okay, thank you everyone for joining. So today we have one of our own PhD students, Sarah. She works in the team of Connie Arts and she's specializing in spectroscopy of BAF stars. And this is a type of research that normally takes quite a bit of manual labor, but she also was involved in trying to automate things. And she will give a talk on combining that spectroscopy with photometry and asteroseismology. So please, Sarah, you have the floor.
Yeah. Thank you, Joris. So hello, everyone. Thank you for joining this afternoon. First of all, I want to say sorry for the very blurry background picture. It's a picture I took at La Palma while I was observing there a few weeks ago. And this is just to advertise that the Mercator runs are very interesting and you should all take one. Not only do you get to see these very pretty night skies, but you can also observe some very, very interesting targets, which I will come back to later on. Okay, so in this talk, as Joris said, I will talk about combining spectroscopy, photometry, and asteroseismic data for BAF-type stars. So BAF-type stars, I mean the stars lying in this red circle on the main sequence, so main sequence stars, but also a bit more evolved subgiants. For example, in our group, we call these intermediate to high mass stars, so masses from 1.3 to 9 solar masses, and temperatures from 6,500 up till like 25,000 Kelvin. And so for these stars, spectroscopically wise, we don't have a lot of metal lines that are, for lower mass stars, that are apparent in our spectra, and we also don't have to deal with winds that occur in higher mass stars. So we are dealing with the region of stars in between there. So BAF-type stars, like all kinds of stars, you can observe them in many different ways. One of them is spectroscopy. So with spectroscopy, we can get surface properties of these stars, such as effective temperatures, surface gravities, the velocities of the stars, broadening mechanisms, the metallicity as well, and individual abundances. For my work, for the spectroscopic data, I've been using Hermes spectra, so taken with our own spectrograph, and also Ferros data, which is a spectrograph that is attached to the 2.2 meter telescope at La Silla in Chile. Another type of data is photometry and astrometry. So with that, we can get magnitudes, colors of the stars, and if we at distances, we can also get luminosities. And as many people do, I'm using Gaia data for that. And then the last part, asteroseismology. As opposed to these others two, we can get internal properties of the stars with this observation, with this methods, such as the mass of the convective core, radii, the mixing properties and rotation processes that are happening in these stars, and also ages. And for that, people mostly use Kepler and TESS data. There are other ways to observe these stars, such as if you happen to have an eclipsing binary, you can get really good constraints on masses and radii. If stars happen to be in clusters, you can get ages and compositions, and there are many more techniques, but I'm not going to go into those since I am mainly using the three there above. Let's hope this loads. So coming back to this slide, why am I actually grouping all these kinds of stars together, this range of stars? Well, they have a similar internal structure. So they have a convective core, a radiative envelope, and some of them might also have like still a tiny convective outer envelope around them. And what's really interesting for these stars is that there are gravity modes propagating in these stars that are visible on the surface. And so in this region, there are two large main groups of gravity mode pulsators, which are the gamma dors and on the lower mass side, so F and late A-type stars. And you also have slowly pulsating B-type stars on the higher mass end. As I said, gravity modes, they probe the near core region. So we can get information about processes that are happening in this region inside stars. I'm not going to explain this in too much depth because there are a lot of asteroseismologists here that know a lot more about this than I do. But quickly, so what people do is they get a nice light curve, preferably from Kepler or TESS. They perform a Fourier transform on that spectra, so they get this amplitude versus frequency or period in this case. Then they identify certain peaks in this diagram, and they get a pattern like here below. So there you have on the x-axis still the periods, and on the y-axis you have the difference between consecutive periods here in this diagram. And so these are the patterns that asteroseismologists they analyze, so they can get a lot of information out of it, such as you can see on the right side here. I mainly want you to focus on the different colors here in the pattern. So these are period spacing patterns for different rotation rates. So if you can see that the patterns have a different tilt based on the rotation. So by looking at the rotation of these period spacing patterns, you can get information, you can get an estimate of this near core rotation rate. And while this is really interesting, this is also the way that people detected there is a problem with the theory of stellar structure and evolution. Namely, as you can see, so this diagram has surface gravity, so an estimate of h on the x-axis, and the near core rotation rate on the y-axis. The gray and purple are main sequence stars, and then you get subgiants and more evolved stars here. And what is interesting, so on the main sequence, here you have circles are core rotation rates and triangles envelope rotation rates. So you see that they are almost the same, so they are near rigid rotators. But if you go to the more evolved type stars, you see that the core rotation rate has decreased by a lot, and it's actually much more than what is predicted by theory. So there is some kind of mechanism happening that causes the star to lose a lot of angular momentum very efficiently, and it's not yet understood what this is. It might be internal gravity waves or magnetic fields, but we don't really know what it is. And in order to study this a bit more, it is really important that we combine observations from asteroseismology with information from surface properties, from surface abundances, for example, so we can get knowledge about the mixing that is happening in these stars. Another problem that is detected is the mass discrepancy problem. So this is by studying eclipsing binaries. People can get estimates of masses in two different ways. So you can get the dynamical masses, which is just from studying, analyzing the binary orbit. And you can also get evolutionary masses from models. And here, so this is a very famous example, this binary star. You have the primary and the secondary here, based on observations. And then there are various evolutionary tracks computed from models. And you can see the black ones are the models computed for the mass that was found for these stars, the dynamical masses. And you see that they absolutely don't agree with the observations. And that a lot of extra mass, like the red tracks, is by increasing the mass is needed. And you also need a lot of interior near-core mixing to match the dynamical and evolutionary masses. And it's not really understood, again, how this is happening, where this additional mass is coming from. Is it from adding fuel to the core by more mixing in this region? It's not really known. And so to understand this, we again should combine asteroseismic data, spectroscopic data, and binary observations together. Now, some last examples before I start boring you. So here in the left plot is a comparison between spectroscopic parameters and parameters determined from SED, so from photometry. And you can see that here again, there is a large discrepancy between the two observations. On the right-hand side is an example for a bit lower mass stars, where we compare spectroscopic and asteroseismic surface gravities, and you can see that there are some trends in there. It's not exactly the same. So this is pretty weird, because actually we're observing the same star, the same light that is coming from the star, and we analyze them in different ways with different techniques, and we get different results. So something is going on there, and we should try to solve that. So I hope that I could convince you that we need to combine all the observational data that we have available in order to test and improve upon the theory that we have, and to see what we can learn from each of these individual analysis techniques. So for the rest of my talk, I will first go into the three main observations that I use and which kind of methods I use for them. Then I will talk a bit about how I combine these data with the framework that I'm developing to combine the three of them, and some future applications for that. So first, spectroscopy, which is the type of data that I've been working with most during my PhD. So there are different kind of ways to analyze spectroscopic data. One of them is by using the curve of growth and equivalent widths of from the spectra. But I haven't really been using that one. I've been mostly looking at spectrum synthesis. So what is that? You compute synthetic spectra from atmosphere models and radiative transfer codes, and you compute that for various combinations of stellar parameters, of surface parameters, and then you just combine the observed spectrum with each of these synthetic ones and try to find the best matched, and you have your parameters for the stars. Of course, there are various kind of input physics that go into these models, into making these synthetic spectra. You can have models that rely on local thermodynamic equilibrium, LTE, or you can have non-LTE models. There's also a choice between one-dimensional or three-dimensional geometry of the star. And the code that I've been using is one that you probably all know about, is the Grid Search in Stellar Parameters, or GSSP, which was developed by Andrew. And that is a 1D plane parallel LTE spectrum synthesis code. So how are spectra actually formed? Where do they come from? So when you observe a star, you have the continuum of the star, and then lines that are formed in a photosphere around the star. Then the light travels through the ISM. It goes through the Earth's atmosphere, so you get tellurics in your spectrum, and then it goes through the instruments, and you get the spectrum. However, this last part, the instrument, is really annoying because it introduces a response function into your spectrum, so it gives it a certain shape, and it's different from instrument to instrument. So as you can see here, I've plotted a Hermes and a Ferris spectrum, and it's not straight. There's like this slope in here, and there's also some wiggles in the Ferris spectrum. And that's really annoying, because if you want to compare it to synthetic spectra, these are normalized spectra, so you have to kind of get this shape out of the spectrum. What people mostly used to do is to normalize spectra manually. So they select points in the regions of the spectra that they assume is the continuum of the star, and then they fit a spline or a polynomial through these points, and then they divide the spectrum by this spline. And then you can get something that looks like this. So on top, I have selected points, fitted the spline, and then on the bottom, you have the normalized spectrum. But if I would have chosen, instead of the points before, these points, which is maybe a bit exaggerated, but it's not always clear how far you should go into the wings of these lines, so it could be that it's here, maybe. And then you get a really different normalized spectrum. So if I switch between the two of them, you can see that there's really a big change in the normalized Balmer line that you see here. And that obviously, it affects the stellar parameters, the surface parameters that you will determine for this spectra. So to show that here, I've plotted synthetic spectra, where I fixed all the parameters to same values, except for on the left side, I changed temperature, various values for the temperature, and on the right-hand side, there are different values for the surface gravity. And you see what kind of effect it has on this hydrogen line here. And so what I want to say is that the normalization is really degenerate with the effective temperature, surface gravity, and metallicity that you will get for a star. And this is also really dependent on who does the normalization, so different people will deal with differently. Even when you have seen many, many spectra, it can still be that you're doing it wrong, and you won't do it the same for different stars. So there will always be some kind of manual error that you get in your spectrum in this way. And so what Ilya and I, so Ilya, who was also a PhD student here, we have been working on automating this and to making it more robust, so that if we analyze many, many different stars, we normalize them kind of the same way, so that we have the same analysis for all of them, and there is no subjective manual interaction anymore. And for that, we created something that we call the Zeta pane. It's an automation of spectrum analysis, and so one of the benefits is also that it's not a star-by-star approach, but you can use it for very large samples of stars at the same time, and as I said, it includes normalization of the spectrum. How does it work? So we compute a lot of model spectra. In our case, we used GSSP to compute these synthetic spectra, and we created a 5-dimensional grid for these 5 main surface parameters. And it is like quasi-randomly covering the ranges of our parameter space to have a good coverage, which is not totally random, but still feasibly to compute. And then we train a neural network on this grid so that we can create some kind of interpolator. So this interpolator can predict any kind of synthetic spectra with any combination of surface parameters as long as it is within the boundaries of this grid that it was trained on. And then you can just predict synthetic spectra with this interpolator, compare them to the observed spectrum, and you get your atmospheric parameters out. But as I said, you still have this shape in the spectrum. So what we do as well is we include fitting for the response function. So we assume that it can be represented by a Chebyshev polynomial with a certain amount of coefficients. And we add these coefficients as fitting parameters, and we fit them simultaneously with the atmospheric parameters in order to have the best normalization of the spectrum and the best atmospheric parameters at the same time. So this method was recently published by Ilya, and we also did some testing for that. One of the tests was to see how big our grid needed to be in order to get decent results. For that, we computed training grids for various number of spectra, and then we computed some more synthetic spectra that we induced some noise and a response function in them randomly, and then we let each of these neural nets predict the parameters for those spectra and compare them to their real values. And here you see that around 5,000 spectra gives us more or less decent results. At least in most of the parameter space, we found that for low temperature, low V-sin I spectra, it wasn't working that well because these are spectra where there are many metal lines appearing. They're slow rotators, so they have many narrow lines, and the neural net has to be able to resolve all of them, which was not the case with just the 5,000 spectra quasi-randomly distributed. So we added 5,000 spectra more in this low V-sin I, low T-effective regime, and then it seems to work pretty well right now. Another test we did was we looked at the internal uncertainties of the spectrum, so uncertainties that are intrinsic to the modeling framework. So they have to do with the prediction of the synthetic spectra by the neural nets, how good the interpolation works, and also how the minimization algorithm is able to find the global minimum in the end. And for that, we computed 1,000 synthetic spectra, which were not present in the sample that we used for training. We added noise, some Poisson noise, a radial velocity shift, and a response function. And then again, as I said before, we let the pane predict parameters for them and compare them to their real values. And here in this figure, you can see like the differences that we got in each of these parameter values in function of temperature and in function of V-sin I. And you see there are some trends in there. So for higher temperature stars, we get larger uncertainties, which is expected. But the main thing that we got from here, so we averaged those differences out, and then we took that as internal uncertainty on our methods. If you compare that to the statistical uncertainty, so the uncertainty you get just by from the method itself, then these are much lower than the internal uncertainties. And so in literature, often only these ones are quoted. So you should be careful and always take into account that the modeling framework itself also has some kind of uncertainty of its own. So we applied this neural net already to some high resolution spectra, to 2 samples. The first one is a sample of Kepler pulsators, gravity mode pulsators, for which we have Hermes spectra. So going back to the figure I showed before, these are actually some of the stars that are present here, so from the main sequence stars. So we have Gamma Dor and SPB stars in here, and we only took the ones for which we have near co-rotation frequencies determined by asteroseismology. And we looked in the Hermes database, and we found for like 100-ish of them high signal-to-noise spectra. And so I've analyzed those with the zeta pane. And just to show you how well this performs, here are some of the fits that we got. So the blue are the observed spectra, and the orange are the fits. just to give you an idea of how well it works. The other sample that we analyzed are B-type stars, for which Dominic and Mai, they found a large amount of different types of variability in their test light curves. So they used the first 3 sectors of test data to detect variability. And then we applied for observation time at the with Ferrous, and we got a lot of spectra from them that we analyzed with the Zeta pane, and also like we were 3 years later than those papers were published, so we did a reclassification of all the test data that were available like a year ago. Some of the results I show here. So on top, there's a very nice fit for a main sequence B-type star. However, there were also some BE stars in our spectrum, so stars that have emission lines in the Balmer lines. And unfortunately, GSSP is not able to predict synthetic spectra with emission lines there. So we just masked them out. And so the result that we got for these stars are like obviously not very, we can do better. Let me put it like that. And then here on the bottom, you see a fit that is not really well. So here, if I give you a zoom in, you can see that many of the lines are just not present in the synthetic spectrum. And we actually found that these are chemically peculiar stars, so they have overabundances of mercury and manganese in them. So we found 13 of them in the sample. The most important result from the paper, however, is shown in this plot. So here you have an HRD where we put all the stars in them, and we mark them, so the different symbols are different types of variability. There are some tracks to guide your eyes, so for different masses. And this red shaded area is the region where we assume that SPB stars should lie, so the SPB instability strip. And then this line here is the outer edge of the delta Scuti instability strip. If you look at this zoom in, however, you can see that many SPBs, so the triangles, are lying outside of their instability strips. And we found that these are fast rotating stars. So you can see here the V-sin I that we get for them is above 100 at least, and for some of them even higher. And so these are fast rotating SPB stars. So there is the gravity darkening effect that's playing a role. That so your star becomes a bit oblique, and the temperature that you observe is actually lower than the real than the temperature at the poles, for example, of this star. We also found that the frequencies from the test data are also shifted to higher frequencies, which is also an effect of this fast rotation. Okay, enough about spectroscopy. I'll quickly go over photometry, because this is still work in progress. So how I'm gonna fit photometry is just by comparing magnitudes, observed magnitudes with model magnitudes. For the observed magnitudes, that just means that we have to convert the apparent magnitudes to absolute magnitudes using the distance and the extinction value. Still figuring out what is best to use here, so no questions on that, please. For the model magnitudes, it's just, this formula here, where it depends on luminosity, and you have also, you have to take bolometric corrections into account, which depend then again on temperature, surface gravity, metallicity, also different ways to do that, so also still work in progress. The asteroseismology part is also not done yet, but the idea is just to, so this is again the period spacing pattern, like an example that I showed before, where we just try to fit a model pattern to the observed pattern, and hence you get the best fitting parameters out of it. So that's the idea in the end. How am I going to combine all this data? For that, I'm using a Bayesian framework. So for those of you who don't recognize this, this is Bayes' law. So what is important here is X are the model parameters. In our case, we're using mass, age, metallicity, and 2 types of mixing values. And O are the observations. So spectroscopy, photometry, asteroseismology. On the left-hand side, you have the posterior probability, so the probability that you get that a set of parameters is true given the observations. And on the right-hand side, you have 4 terms. So the first is the prior, so it's the prior information that you have about the model parameters, which comes from stellar structure and evolution models. So for example, initial mass functions will come in here. And then you have a spectroscopic likelihood, so that's by fitting the spectra. You have a photometric likely part, fitting the magnitudes, and an asteroseismic likelihood fitting the period spacing patterns. And just combining all of them together will give you the final best fitting parameters. One thing I should mention here is that the parameters that we want in the end are not the parameters that we get from observations. So from observations you get temperatures, surface gravities, magnitudes, stuff like that. But what the models give us are masses, ages, metallicities, mixing parameters. And so we need to go from one to the other. And for that we're using a grid of MESA models. I have computed a new grid with these parameter ranges. So masses, as I said, the BAF-type regime. I'm going a little bit higher even, just in case someone else would like to use this grid. So if you're interested, come talk to me. For ages, we go from pre-main sequence to the end of the main sequence. There are also, we are planning to go a bit beyond, so go to core, end of core helium burning, but that's still work in progress. Metallicities we cover from SMC to galactic metallicities. We have a free parameter for the mixing in the core boundary layer, and we also have a mixing parameter for envelope mixing, for which we assume an internal gravity wave profile. I wanted to show you the actual grid that I've computed, but unfortunately copying files from VSC to the stir disk take a bit longer than expected, so here is another grid for which that I have been using for testing purposes. So the next 3 slides are based on this grid. First, a little bit more about how this actually works. So we use Markov chain Monte Carlo, which means that we initialize a number of walkers, say n, randomly over the grid ranges. So here you can see the black ones are the grid ranges, and the colored dots are the starting positions of the walkers. Of course, you have the other dimensions as well, but it's not shown here. It's just a nice coverage of the whole range there. And then for each position, you compute the posterior probability. So you first convert masses, ages, mixing parameters by interpolating the MESA model to temperatures and surface gravities, and then we compute synthetic spectra with those parameters compared to the observations, same for magnitudes and same for the period spacing pattern. You get a value for the posterior distribution, and then the walker takes a certain step in some direction and does this whole thing again. So that goes for a number of iterations, which it's a free parameter. You can choose how many iterations you want. And then in the end, you hope that this converges to the best solution, so that they walk to the best solution in the grids. I have done some tests for that. Disclaimer, however, this is only using the spectroscopic part. And these are some of the posterior distributions for one star that I got, and the fit of the spectrum. Fit looks pretty nice. The distribution's also pretty nice. But as you can see, the uncertainties that I'm getting are really unrealistically small. I don't know where it is coming from. Like for metallicity, for example, it was even so small that they just put 0. Is this a fact that it's only statistical uncertainties, no internal uncertainties of the methods are taken into account? I've also, in this figure, it's just a part of the spectrum, really zoomed in, where you see like the orange line is a fit, and the little gray area is the uncertainty that like the spectra, possible spectra I get within the uncertainties, which is really small. It doesn't even cover the whole uncertainty range of the observations, so is something going wrong there? I don't know. Still figuring that out. So now for the applications of this framework, the reason why I'm building all of this. So as I said before, if you remember the problem that we have with stellar structure and evolution theory, that the core rotation rates are way lower than expected from theory. this finding was based on only like a few hundred stars. And of course, you would like to expand it to many, many more stars. And we have spectra available for many, many more stars, but they're all most of them are in low resolution surveys. And while these are very nice, if you compare the quality of the spectrum that you get from low resolution spectra versus what we can get with Hermes and Pharos, you can see that like the number of lines is limited. There are a lot of blends in there, so you can get less precise information out of them. And what we want is to calibrate, like create a calibration sample with high resolution spectra so that we can calibrate these spectra in these low resolution surveys and try to get as precise parameters for these low resolution spectra as for the high resolution spectra. Still not sure how this will be done. We probably will need some machine learning AI methods to do this. And so for I call this a golden sample. We have all kinds of information, also photometry and astrometry and asteroseismology available for these stars in low resolution surveys. We will probably not have all of that data, so we'll have to deal with incomplete data, and so it will be a challenge, let me say it like that. So coming back to what I said on the first slide, so here is the golden sample that I've constructed. It contains a lot of stars for which we have Pharos data, but there are also, like the purple ones are Hermes data. So please, if you go observe program 1 to 121. It's very nice. And so with that, I have come to my conclusions. So I hope that I've made clear that we really have to combine all kinds of observational information to make sure that we get consistent results and so that we can test theory. I have introduced you the Zeta pane, so a new automated approach for spectrum analysis that includes normalization, which makes our life much easier. I have touched a bit upon the Bayesian framework that I'm developing with MCMC to combine all this data. And I've also hinted upon like the golden sample that I'm constructing with a calibration sample for large low resolution spectroscopic surveys. So thank you very much, and I'll take any questions that you have.
Thank you very much, Sarah. Very nice talk. Are there any comments, feedback, questions?
On the slide with the unrealistically small error bars, is there a dot missing in the error bar on the H then as well? Because that doesn't seem to be very, very small. Because the H in mega years...
Probably, yeah.
Because
sorry.
It's plus 135 mega year.
Yeah, sorry. I converted this from years to mega years, and there probably something went wrong there. Yeah.
Yeah, it's like, okay, that's like... Okay,
yeah, the number is there as well, right?
Yeah.
Okay. Yeah, sorry, mixed up there.
Sarah, I have a question with respect to your spectral modeling and grid. You scale with metallicity, but at the end is the need not for more detailed abundances? So like alpha enhancement or whatever impact. So if you have a connection between the core and the envelope, your surface abundances will change, but not necessarily just the scaled metallicity, but also some more specific elements will enhance and other ones.
Yeah, our Zeta pane only includes these 5 dimensions. That's also future work. We will try to add more individual abundances, individual elements in there, but it's not that difficult to do, but there will be a lot of testing involved to see how large the grid should be in order to have decent interpolated synthetic spectra. It's possible. It will probably happen within this and a few years.
No, but the question is whether your atmospheric, let's say, temperature gradient or density gradient is dependent on the alpha enhancement. Probably not for just minor abundance changes, but I can imagine that if alpha is enhanced, your stellar atmospheric structure will change, and hence your method will not be just scaling metallicity. That's it.
Yeah, I'm not sure if I'm really following there, but I might.
So while fitting, in your fit, you include fits of the Balmer lines, which are dependent on the temperature structure and density structure of your atmosphere. But if that is impacting. So the metallicity is important, but maybe also just alpha enhancement can also change the atmospheric gradient, and that hence will change your value of effective temperature and gravity because you don't take this into account.
That's true, but then that's also the case with the normal version of GSSP, right? Or am I not understanding this correctly?
Sorry? Yeah. So it's really the physics of the atmospheric structure that is changing.
Yeah.
Yeah.
Thank you. Thanks for this great talk, Sarah. This is maybe just, I'm just curious, like, because you are turning into like a Bayesian framework, but do you expect to experience any problems in the future when you're running this many stars for your golden sample? Because Bayesian statistics is heavy, right, compared to frequencies.
Like testing sometimes takes 1 hour for one star already, and that's only including spectroscopy. So yeah, as we discussed in the GATCAP before, like speeding up all these scripts will be very interesting.
You will fill up the VSC.
Yeah.
Any more?
Thanks. Thanks, Sarah. Wanted to ask you, what is the temperature range of the GSSP models?
Well, we use 6,500 till 25,000, but GSSP can go lower, I think, if I'm not mistaken.
Lower, you said?
Not sure. I'll have to look it up, but I think it can go lower.
But you don't go to higher temperatures?
No, but it's also possible. Like this method, we just computed the neural nets based on a grid for our needs, but you can recompute the grids with any range of temperatures using GSSP or another codes, and you can just apply the same methods, like train the neural nets on this. I have the code somewhere. I'm not sure if it's publicly available, but if you're interested, I can definitely pass it on.
Definitely. Thank you.
Any more questions?
Hi. I was just wondering, and when you're talking about, for the low resolution samples, so there are existing like codes out there, like the Canon, for example, that do things like label transfer. Is it a similar methodology that you're looking to apply, or is this a like same methodology with like a better sample essentially? So instead of using apogee, you'd essentially.
That's a possibility, yeah. We'll still have to look into the various options there, but the Canon, I think the pane is even a bit based on the Canon. So the pane is the original algorithm where we based the zeta pane on.
Okay.
And so I think Canon is more data driven.
Yeah, it's
and
entirely data
well, the
driven.
pane is a model driven approach there.
Yeah. Okay. Cool.
Yeah.
I was just wondering what the
Yeah.
distinction was going to be, but that makes sense.
Thanks for a very nice talk. In your modeling, both in spectroscopy and in future in asteroseismology, you use very high dimensional grids. And you have different methods of going through them. You have the neural nets, you have MCMC in future or currently. Can you tell us a bit more about the choice that you make for these different methods? And second question related to that, if your dimensions increase, in your opinion, where should we look? Because that's going to be a bigger problem in the future for all of us. Thank you.
Good questions. So first of all, like the Bayesian framework and the MCMC, that's for all of the different observations, right? I don't know if you understood me correctly or I misunderstood you.
No, I'm thinking more along in terms of a practical sense.
Yeah.
So Bayesian, you can do a statistical framework, but you also use the neural nets, so machine learning. Then you have MCMC. So we always have the trade-off, the number of dimensions and the number of data and models that we want to handle and the required computation time.
Yeah.
So given that we keep increasing the amount of physics that we put into our models, I'm curious what your opinion on that is.
Well, I think if we want to get more information about mixing, we should definitely go for various more abundances, different elements. So that would have to increase the neural nets. I don't think we we have to do something for on the modeling side for that, because you just have output already from the MESA. If you output abundances, you can match them. Well, it will all depend on what we find, of course. Like if we find some weird things in theory and we have to adapt, like compute models for different input physics, then then you have to go look there and I don't know.
Yeah, I'm sorry. Okay. Let me see if I can. I know my question is very vague, so let me see if I can rephrase. It's more along that I was more curious about the methodology. So, okay, let me put it like this. Why do you choose in one case a neural net? Why in another case MCMC? And are they equivalent, or would you choose something else in future? I'm sorry, I know it's not an easy question to ask, but I was curious.
But like the neural net is just to predict synthetic spectra, while the MCMC is just to go over the mass and age ranges, and you also do that for the spectra, for example. And then you just, at that point, you let the neural net predict a synthetic spectrum. So it's actually, this neural net is the same as if you would just have a grid of GSSP models. So I don't see the problem with that, actually. It's just a fast interpolator instead of you having to increase the how do you call this? Yeah, to go more into depth in the GSSP grid. So like sometimes you have to compute it multiple times to get how do you say this? What's the word? To get a better resolution, actually, of the parameters. So this neural net is just a fast way to get synthetic spectra for any value of the parameters. While the MCMC is just combining the three types of data. I see what you mean. Why we don't use just a neural net for that, maybe, or
not in that sense. I can see why you would, or I can see that you would want to test different methods, but we can talk more offline about this. This may be easier, because I think this may be a bigger discussion than just a question after the seminar. Thank you.
Okay, I'll ask the last question myself. So for radar wavelengths, you're heavily affected by tellurics. Is setup pane able to take this into account somehow, or?
At the moment, I have only been using a wavelength range from 4,000 to 5,800 angstrom, so no tellurics, or not in that region. We could go further, but the pane currently does not take that into account.
Okay, yeah, thank you. Okay, so no questions anymore, so thank you very much.
Thank you.